Welcome to the Deep Dive, the place where we turn these massive, often intimidating technical reports into knowledge you can actually use. And today, we are opening up the Modern Adaptation Handbook to look at, well, how we actually steer the biggest, most powerful AI models in existence. Because the core of AI is just profoundly shifted, hasn't it? It's no longer about designing neural networks from the ground up.
Not at all. That entire field of architectural engineering has given way to what you could call context engineering and parameter adaptation.
That's the critical pivot.
It is. These foundation models, whether they're for text or vision or audio, they hold this vast amount of latent knowledge. They're generalists. The real trick is getting them to specialize efficiently. And the challenge, frankly, is just the sheer size. A 70 billion parameter model is the new benchmark, but it needs astronomical resources just to load.
And that's where we come in. Our mission today is to unpack the analysis from this handbook. We want to understand the key breakthroughs in parameter-efficient fine-tuning, or PEFT, in model alignment, and the very exciting rise of multimodal systems. We're going to show you the specific shortcuts that are democratizing access, so you can steer these giants without needing a billion-dollar data center. Okay, let's unpack this. To really appreciate how brilliant the new methods are, we have to start with the old problem, full fine-tuning, or FFT. Why was it such a non-starter for basically everyone? There was this crippling dual cost, right?
Oh, absolutely. It was a hardware tax and a knowledge tax all in one. Let's just talk hardware first. For a relatively small 7 billion parameter model, the weights alone are about 14 gigabytes.
Yeah.
But for training, you need 4 to 6 times that. You have to store the gradients, the optimizer states, usually Atom W, and all the intermediate activations. Suddenly, that small 7B model needs well over 60 gigs of VRAM. It's immediately out of reach. It's enterprise only.
And the knowledge tax, the technical cost, that was almost worse than the hardware cost, wasn't it?
It was. It's this problem called catastrophic forgetting. FFT updates every single parameter in the model. So when you force these huge updates for a very narrow task, you overwrite the generalist reasoning it learned during pre-training.
You turn a genius into a specialist who's forgotten everything else.
Exactly. Its core versatility is just gone. And that's why low-rank adaptation, or LoRA, became so foundational. LoRA is built on this really simple insight. The change in the weights, the delta W, doesn't need to be high-dimensional. It has a low intrinsic rank. So instead of touching the original weights, you freeze them. And you inject 2 tiny trainable matrices, A and B.
And you only train those.
You only train those 2 little adapters. You can reduce the number of trainable parameters by, up to 99.9%.
That is just genius. You sidestep catastrophic forgetting by only adjusting the steering wheel. You leave the engine alone. But how do you take that concept and get it to work on the 70 billion parameter models, and crucially, get them onto consumer hardware? That's where QLoRA just completely changed the game.
QLoRA, or quantized LoRA, is the big memory breakout because it attacks the other half of the problem, the frozen base model itself. QLoRA quantizes that massive base model all the way down to 4-bit precision. But, and this is the elegant part, they didn't just use standard 4-bit integers. They introduced something called normal float 4, or NF4.
Okay, wait, hold on. If you quantize the base model to just 4-bit, doesn't that introduce a ton of noise? Doesn't that just kill the accuracy right away?
That is the million-dollar question, right? And it's why that NF4 format makes all the difference. Think about it. Most neural network weights, they cluster really heavily around 0. They follow a normal distribution.
Right.
So NF4 is a nonlinear data type. It cleverly allocates more of its very limited 4-bit quantization bins right around 0. It maximizes information density exactly where the important data lies, which reserves performance while just slashing memory usage.
That is clever.
And QLoRA added 2 more tricks. Double quantization, which just means they compress the quantization constants themselves to save a bit more memory, and paged optimizers, which offload optimizer states to system RAM when your VLAM spikes. You combine those 3 things, and that's how you get a model like Llama 370B fine-tuning on one high-end consumer GPU.
That is the very definition of democratization for high-end AI. But even with QLoRA, the handbook notes there's this persistent performance gap compared to true FFT. What was LoRA missing? What was the subtle geometric complexity?
It really comes down to separating movement. So think of fine-tuning a weight like moving a boat. You can change its speed, that's the magnitude, and its compass setting, which is the direction.
Speed and direction.
Right. Full fine-tuning lets you change those 2 things independently. It gives you maximum control. But standard LoRA forces them to change rigidly together. It's like having a volume knob but no equalizer. And this limitation led to DoRA, weight-decomposed low-rank adaptation. DoRA formally decomposes the weight matrix W into a magnitude vector, M, and a directional matrix, V. And the key step is it applies the LoRA updates only to the directional part, to V, while the magnitude M is trained on its own.
Ah, so it decouples them.
Decouples them. And that successfully mimics the more nuanced learning dynamics of FFT.
So if LoRA was the volume knob, DoRA is the volume and an independent EQ. And the state-of-the-art in 2025 is the fusion of the two, QDoRA.
Precisely. QDoRA takes QLoRA's efficiency and combines it with DoRA's superior structure. The NF4 quantization is applied to that big directional backbone, which saves all the memory. But that independent magnitude vector, M, that's kept in higher precision, it acts like a protective buffer. It absorbs the quantization errors from the 4-bit backbone.
So you get FFT-level accuracy on budget hardware. That's the takeaway.
That is the definition of it.
Okay, that is the technical foundation. Now, moving from theory to practice, implementing QDoRA, or any of this, requires specific tools. If a listener wants to get started today, what are the 3 big libraries that make this practical?
The first one you have to know is the efficiency engine, Unsloth. They don't just rely on standard frameworks. They use manual autograd and custom Triton kernels to rewrite operations, fusing them together, which cuts down on memory fragmentation.
That gives you a huge performance boost, right?
Huge boost, up to 2x training speed over the conventional way of doing things.
And their benchmarks really show the impact. They mention that Unsloth can fine-tune a Llama 3.8b model with a context length of over 100,000 tokens on a standard 48 GB GPU. That jump in efficiency, being able to process that much context, it dramatically changes the kind of problems you can even attempt to solve.
Absolutely. The second library is TRL, Transformer Reinforcement Learning, from Hugging Face. This is more the generalist toolkit. It abstracts away a lot of the complexity with these high-level interfaces, like the SFT trainer or the DPO trainer.
So it's easier to get started with.
Much easier. And if a new method drops tomorrow, TRL is probably going to support it within a few weeks. It moves fast.
And finally, for anyone in production where you just need perfect repeatability, you've got Axolotl and Llama Factory.
Right. Their whole philosophy is reproducibility. Axolotl uses these comprehensive YAML config files to define every single part of the training run.
So what you run on your machine can be perfectly replicated somewhere else.
Perfectly. And Llama Factory just puts a web UI on top of that same philosophy, which lowers the barrier to entry even more.
So now we have the efficient tools. Let's talk data, because the data structure is just as critical as the content, isn't it? If you feed the model the wrong format, the fine-tune just fails, no matter how good your PEFT method is.
It's garbage in, garbage out. You have to match the data format to your goal. For single-turn tasks, the simple alpaca format instruction input-output is fine. But for building a chatbot, it's useless.
Because there's no history.
Exactly. So the standard for that is the shared GP2 format, which is a list of messages that preserves the conversation history. The tools then use what are called chat templates to serialize that JSON with the correct separator tokens the model expects.
And since high-quality human data is so scarce, we're all relying on synthetic data now. How do you make sure the quality is there if the model is just teaching itself?
That's where you have to be rigorous. It's a 2-stage process. First, you have a frontier model generate instruction response pairs, often making the instructions more complex with something like evil instruct.
And then comes the crucial step.
Then comes the safety step, consistency filtering. A separate judge model evaluates all those generated pairs, maybe 10 million of them. And it only keeps the tiny fraction that meet really strict criteria for factuality and sound reasoning. This is how you get quality assurance in a self-teaching loop.
And a key takeaway here is just how fast this all is, which is a huge relief compared to pre-training.
Oh, it is. Pre-training runs for trillions of tokens. Fine-tuning is usually just 1 to 3 epochs. If you go beyond that, you risk overfitting and just memorizing the data.
And I noticed the learning rate is pretty aggressive too, something like 1E-4.
It is, and that's because you're only training that tiny set of parameters, the LoRA adapters.
Yeah.
So they need a bigger, faster push to actually influence the frozen weights.
Okay, so we've solved how to update the parameters with things like QDoRA and Unsloth, but that efficiency doesn't mean anything if the model says the wrong things, if it's not safe or helpful. That brings us to alignment. RLHF used to be the standard, but it was so complex with 3 different models. How did the community stabilize that whole process?
It's incredible how fast the field moved on this. Everyone quickly converged on direct optimization methods, specifically DPO, direct preference optimization. DPO just skips the most unstable part of the old system, which was the reward model.
How does it do that?
It basically reframes alignment. It's not a complex reinforcement learning problem anymore. It's a simple classification problem. The DPO loss function just compares the likelihood of the chosen good response to the likelihood of the rejected bad one.
So instead of training an AI judge to score things,
You just teach the model to directly prefer the good reply over the bad one. It's far more stable and way simpler.
but DPO still needs paired data, right? A chosen and a rejected reply for the exact same prompt. What if you're a company with, I don't know, a huge log of good customer service chats and a separate list of complaints? The data is all there, but it's not paired up.
And that is the absolute elegance of KTO, Kahneman-Tversky optimization. It uses a psychological model prospect theory, specifically loss aversion, to work with that messy, unpaired data.
So it's using human psychology.
It is. KTO knows that humans are more sensitive to losses than gains, so it assigns a heavier penalty for bad outputs than the reward it gives for good ones. That bias towards avoiding failure lets it learn alignment even when the data isn't perfectly structured. It's a huge deal for enterprises with existing logs.
Incredible. And even DPO and KTO are now being pushed further by ORAPO.
Yeah, ORAPO, or odds ratio preference optimization, is the next step in streamlining. It's the single-stage solution. It takes that preference penalty and just integrates it directly into the supervised fine-tuning loss function.
Which
Which means you don't need a separate reference model at all. You save 50% of the VRAM that DPO requires. If VRAM is still your main constraint, ORAPO is the powerhouse.
So to summarize the alignment landscape, DPO is the stable workhorse,
Yeah.
KTO is for your messy enterprise logs, and ORAPO is the ultra-efficient low VRAM solution. We have options.
We have options based on data and hardware. That's the theme.
We focused on text, but the sources make it very clear that 2025 is about models that process sight and sound too. What are the unique challenges when you step into multimodal LLMs?
With MLLMs, the number one challenge is modality imbalance. The LLM backbone has such a strong prior for language that it overpowers the visual signal.
And that leads to?
It leads to the classic flaw of early MLLMs, visual hallucinations. The model describes things that are definitively not in the image.
The model is thinking in words and ignoring its eyes. So what's the technical fix for that?
The handbook points to a method called more as modality linear representation steering. It introduces these specialized learnable steering vectors right into the LLM's intermediate layers. And these vectors are trained specifically to amplify the visual features.
Just like turning up the volume on the visual input.
Exactly. It forces the LLM to pay attention to what it's seeing, which significantly cuts down on those hallucinations.
And I imagine the data engineering is different too. The files themselves must be structured in a specific way.
They have to be. The standard is the lava JSON format, which has to seamlessly interleave text with image placeholder tokens, like image. And to really test if it's working, you need specialized benchmarks. Things like MMMU, which has expert-level college exam reasoning, or MathVista for analyzing charts and plots.
Okay, so now let's shift to the audio frontier. Text-to-speech, voice cloning. This seems like the hardest challenge because sound is so continuous and high-dimensional.
It has been historically, but unified models are closing that gap. A model like SpeechGPT addresses this by treating speech itself as a language. It uses a discrete speech tokenizer to quantize the continuous audio into speech tokens.
So it's not a sound wave anymore, it's structured data, just like text.
Exactly, and that means the model can capture things. Text transcription loses paralinguistic features like laughs or sighs or the tone of voice.
And what about real-time conversation?
For that, you're seeing models like StyleTalker for speech-to-speech. It has a parallel style encoder that extracts the emotion and tone from your voice. This lets the system generate its TTS response with an aligned style. So if you sound angry, the agent can respond in a calm, de-escalating tone.
That's incredible.
And again, data standards are everything here. The LJ speech format, WAV files, plus a metadata CSV requires rigorous normalization. If your text says 1990, it has to be expanded to 1990 before training.
Otherwise, the audio-text alignment just breaks.
It breaks immediately.
This has been a fascinating journey. We've gone from the brute force of full fine-tuning to the elegance and accessibility of QDoRA, and from complex alignment systems to the stability of KTO and ORAPO.
And it all reinforces one crucial reality for anyone listening. These advancements are now baked into the software stack. Using tools like Unsloth and techniques like QDoRA, models that used to require an enterprise cluster, that 70 billion parameter giant, can now be fine-tuned on a single high-end consumer GPU. A 48 gigabyte card can do the job.
And once that fine-tuning is done, what happens to those little adapter matrices? Do you get a latency penalty at inference time because of those extra LoRA layers?
No, absolutely not. And this is a key point. Once you're done training, those small adapter weights are mathematically merged back into the base model. It creates a standard, fully fine-tuned model with zero inference latency penalty. Then you can convert it to a compressed format like GGUF and run it locally on a CPU or even Apple Silicon.
So what does this all really mean? The tools and the hardware limitations?
Yeah.
They're essentially solved technical problems now.
That's the clear consensus in the handbook. The limitation has fundamentally shifted. It's not about code and hardware anymore. The bottleneck is now the creativity of your dataset construction and the precision of your alignment strategy. So if efficiency and alignment are solved problems, then the future of AI specialization isn't about deep learning engineering anymore. It's about seeing the world through the specialized data we curate, text, sight, and sound, and leveraging human preference data to instill these models with a truly holistic, specialized understanding. That's something for you to mull over.